calculating inverses with restrictions. Prior to this video, you should have already watched the video where we are finding inverses just in general. And we talked about the two-step procedure that involves switching the x and y value and then solving for y. But now what we're going to do is we're going to take a look at problems that have a restriction. And the restriction actually looks like an inequality statement at the end of the function notation. And so for this case, we see that we're restricting our domain just to be the x values greater than or equal to 0. So what that's actually telling us is that this function that we have, we're only observing one side, if you would, or one portion of that function. So what I did to help make this point for us is we actually went ahead and started looking at the graph a little bit. Now again, you won't have to do the graph, but I'm showing the graph to make a justification why this is actually taking place. So if we take a look at the function, we understand that since it's a quadratic, this would actually make a parabolic shape. However, by only doing half, or the value is greater than or equal to 0, we don't get the full parabola, we only get half of the parabola on one side. And these points were actually calculated here on this table of values. So that's pretty interesting for us to actually see, but it's also going to make sense the more we have an understanding of what the horizontal line test is. Because you're going to learn future that the horizontal line test talks about, how to see if the inverse of a function is actually a function. But that's in another video. Let's get back to ours. So we have our information here. Let's go through the process of actually finding the inverse. So when we find the inverse here, we remember that we switch x and y, and we're going to solve for y. And here's where the interesting part comes up, is since I have a square, I know to solve this, I take the square root of both sides. And upon taking the square root of both sides, I also remember that in the solving process, when I take the square root of both sides, I should have a plus and minus. But here's where our restriction comes into play. What this is actually telling us is we don't necessarily incorporate the plus or minus. This is telling us just to incorporate the positive version of our statement down here. So I actually do not need to put the plus or minus. We're just going to use the positive version of this. And here's what we have. We have y equals the square root of x minus 1. Or in other words, the inverse is equal to the square root of x minus 1. Now what's interesting about this is we can go back and confirm. We see that we had addition, so the inverse has subtraction. We have a square, so the inverse, we have a square root. That checks off. Looks like we're in good shape. But let's go a little bit further with this. We actually have a graphical relationship as well as an algebraic relationship, such that the key again for the inverse is that what we're doing is we're switching x and y. So for the inverse function, we can actually produce the graph just simply by switching our x and y values. 1, 0, 2, 1, 5, 2, 10, 3. If I go and plot this, I see that I have the point here 1, 0, I have 2, 1, I have 5, 2, and then I have the point 10, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the other part that we see happening in this case is that anytime we have a graph, the relationship between a function and its inverse is the reflection about the line y equals x. So what that does is that actually gives us a little bit of a preview for whenever we get into graphing square roots. And when we graph square roots, we can see what the shape might actually look like. And maybe we'll have a better insight to why there was a restricted domain when we start talking about the graphing aspect. But for us right now, when we're finding these inverses, just make sure that whatever the statement says, that's going to tell us whether or not we use the positive for the plus and minus or the negative. because these restrictions will only occur if our original function has an even exponent.